Settle in and let yourself grow heavy. There's nowhere to be now, nothing to do but rest. Let your mind wander to the strange, looping idea of things that never had a beginning. If this quiets your mind, subscribe, and there's always another waiting tomorrow night. The magazine is slightly smaller than a modern paperback. It's paper the color of old cream, the kind that has spent decades in a drawer rather than on a shelf. The cover shows a figure in a silver suit against a background of deep blue, the artist's name printed in a small font near the bottom edge. Above the title of the story, in letters not much larger than the body text, the name Anson MacDonald appears where an author's name would ordinarily go. It is a pseudonym, a borrowed name, a name that belongs to no one in particular. The story beneath it, published in the October 1941 issue of Astounding Science Fiction, is called By His Bootstraps, and the thing it describes has no clean beginning anywhere in it. Robert Heinlein wrote the story, though he did not put his name on it. The plot concerns a man who encounters a notebook. The notebook contains detailed instructions about a future that the man then goes on to inhabit. He copies the instructions. He passes the notebook backward through time to the version of himself who first found it. No one writes the original. The information in the notebook arrives without any point of composition, without a first moment at which someone sat down and set pen to paper in the ordinary way. The notebook simply moves in a loop, its contents intact, its origin nowhere. It is the kind of idea that settles into the mind quietly. There is no drama in the notebook, no explosion, no urgent machinery. There is only a piece of paper and writing on it, and the steady, unremarkable observation that the writing never had an author in the usual sense of the word. The story was not alone in 1941. The pulp shelves of that decade carried dozens of stories about time and its manipulation, adventure stories with clocks and paradoxes, and men running across the pages of their own histories. What made Heinlein's contribution particular was not the adventure, which was modest, but the precision of the loop he constructed. The information in the notebook does not degrade. It does not accumulate errors as it passes through each transfer. It arrives as it was sent, and it was sent as it arrived, and neither version is earlier than the other. That is the specific structure of the bootstrap paradox, not simply a loop, but a loop in which something exists inside the loop that cannot be traced to any source outside it. A reader in 1941, sitting with that magazine open on a wooden table, the room perhaps lit by a single lamp, might have turned the word over for a while before sleep. The idea has a particular texture. It is not threatening. It is more like finding a sentence in a book that the sentence itself seems to have written, a thing that refers only to itself, and yet somehow conveys information. The texture of it is smooth and slightly cool, like a piece of glass that fits unexpectedly well in the palm. 4 years after Heinlein's story appeared in print, the physics of electromagnetic radiation received a proposal that introduced a structure not entirely unlike the notebook. Richard Feynman was in his mid-20s when he and John Archibald Wheeler published their absorber theory in Reviews of Modern Physics in 1945. The proposal was, on its surface, a response to a technical problem in classical electrodynamics. When an accelerating electron emits radiation, the standard equations produced a troubling term, a force the electron exerted on itself, an infinite self-energy that made the mathematics difficult to manage. Wheeler and Feynman proposed a solution that was, in retrospect, more interesting than the problem it addressed. Their suggestion was that electromagnetic radiation is not a single wave traveling forward in time from a source. It is instead a combination, a wave moving forward in time from the emitting charge and an answering wave moving backward in time from the charges that will eventually absorb the radiation. The two waves interfere, and the result is the observable light. The emission and the absorption in this picture are not cause and effect in the simple forward-pointing sense. They are a handshake across time, neither party acting without the prior response of the other. Feynman's chalkboard in those years would have carried the mathematics of this in long, careful lines, the notation precise and slightly beautiful in the way that physics notation becomes when the author has inhabited it for a long time. A single photon traveling outward from a lamp appears, in the absorber theory, as only half of the transaction. The other half moves backward toward the moment of emission, arriving at the source before it was emitted, completing the exchange. The photon is not simply sent and received. It is sent in response to its own reception, and received in response to its own sending. Wheeler went further with these ideas over the following decades. He was a man who followed a line of reasoning wherever it went, and the reasoning led him to several places that required, at minimum, a willingness to set aside ordinary assumptions about the direction of time. The absorber theory was not universally adopted in physics. It remained a minority view, a road taken by few, but its publication in one of the major journals of physics established, in the formal record, that a serious treatment of backward causation was possible and mathematically defensible. That is not a small thing. The notebook had moved from the pages of a pulp magazine to the pages of a peer-reviewed journal. In a laboratory in Orsay in the years beginning around 1980, Alain Aspect and his colleagues were constructing an experiment of considerable delicacy. The question they were investigating had been posed in formal terms by John Bell in 1964, who had taken an argument that Einstein, Podolsky, and Rosen had put forward in 1935, and turned it into a testable prediction. The argument concerned entangled particles, pairs of particles that had interacted in such a way that their quantum states could not be described independently. When a measurement was made on one particle, the other particle's measurement result was correlated with it, even at a distance, even when no signal could have passed between them in the time available. Einstein had found this deeply unwelcome. He used the phrase spooky action at a distance, and the phrase carries, even now, the specific flavor of his objection, that if the particles were genuinely communicating, the communication would have to travel faster than light, which his own special relativity forbade. His preferred explanation was that the particles carried hidden instructions from the beginning, values set at the moment they were created that would determine the results of any future measurements. Bell's 1964 paper showed that this explanation made different statistical predictions from the quantum mechanical one, and that an experiment could in principle distinguish between them. Aspect's experiment was the most rigorous version of that test that had been performed to that point. The particles in his laboratory were photons, generated in pairs and sent to detectors placed some meters apart on an optical bench. The settings of the detectors were switched rapidly, fast enough that no signal traveling at or below the speed of light could have passed from one detector to the other between the switch and the measurement. The results were consistent with quantum mechanics. The correlations were there, intact, independent of the distance and the switching. The hidden instruction explanation did not hold. Two photons on a laboratory bench in Orsay, separated by a distance measured in meters and connected by no visible thread, each settling into a spin direction that the other already knew. The image is restful, in a certain light. There is nothing violent in it. There is only the quiet observation that the information about the outcome appears to exist in both places at once, or in neither place until both measurements are made, or in some arrangement that does not fit cleanly into the vocabulary of signals traveling from causes to effects in a single direction. The physicists who have worked on this most carefully have not arrived at a single agreed description. What they have agreed on is that the ordinary picture is incomplete. The result of Aspect's work did not resolve the question of what entanglement is. It removed one possible explanation. The correlations cannot be accounted for by anything as simple as instructions written into the particles at birth and carried forward through time. Whatever the explanation turns out to be, it will need to accommodate something more unusual than that. The loop, in some form or another, keeps appearing in the mathematics. The mathematics of loops in time had received its most rigorous physical treatment in a paper published in 1949 by a logician who had spent several decades studying the foundations of mathematics before turning his attention to the structure of the universe. Kurt Gödel arrived in Princeton in 1933, having already published the incompleteness theorems that would define his reputation in the history of logic. Albert Einstein arrived there in the same year. The two men became close friends, as improbable a pairing as the mid-20th century produced in academic life, and they walked together often across the Princeton campus in the years that followed. In 1949, Gödel published a paper in Reviews of Modern Physics as a contribution to a volume honoring Einstein's 70th birthday. The paper presented an exact solution to Einstein's field equations, the equations at the heart of general relativity, describing the large-scale structure of space and time. Gödel's solution described a universe filled with rotating dust, a universe turning slowly in a way that had a particular consequence. In such a universe, the geometry of space-time allowed for the existence of closed time-like curves. A closed time-like curve is a path through space-time that returns to its own starting point. A traveler following such a path would move continuously forward in their own experience of time, never reversing, never stopping, and yet eventually arrive at the same point in space-time from which they had departed. Every event in the traveler's history would lie in the past of every other event in their history. The universe, in Gödel's solution, turned so completely that every moment in its history was connected to every other, not by memory or record, but by the actual geometry of space-time. Einstein acknowledged that the mathematics was valid. He found the physical implications troubling, and said so in the same volume where Gödel's paper appeared. The troubling part was not a calculation error. The field equations, which Einstein had derived to describe the behavior of space and time under the influence of mass and energy, admitted a solution in which the ordinary distinction between past and future dissolved at the level of space-time geometry. Gödel had found this not by looking for it, but by solving the equations carefully and noticing what the solution implied. Gödel filling a notebook in Princeton in 1949, the handwriting precise and unhurried, is an image that carries a particular quality. The mathematics was being handed across a shared office wall from one of the most careful logicians in the history of the subject to the man whose equations he was working with. The notebook's contents described a universe with no absolute time direction. The loop appeared again, not in a story this time, and not in a radio wave, but in the deep grammar of how mass bends space. There is a branch of computer science that has also produced structures with no origin, though they arrive by a different path. Unwind is a program that, when run, produces its own source code as output. It does not read a file. It does not receive its text as input. It generates the text of itself from within itself, and when the program finishes running, what appears on the screen is identical to the program that generated it. The Quine is not a curiosity of science fiction or a speculation about time. It is a standard topic in theoretical computer science, one that students encounter in foundational courses, one that professional programmers sometimes write as exercises. There are documented quines in dozens of programming languages. There are quines that produce their own code in a different language from the one they were written in, so that the two programs form a loop in which each generates the other. There are quines so short they fit on a single line of code. There are quines long enough to fill several screens. The theoretical framework for understanding quines was articulated with particular care in Douglas Hofstadter's 1979 book, Gödel, Escher, Bach, An Eternal Golden Braid, which won the Pulitzer Prize for General Nonfiction in 1980. Hofstadter was interested in the phenomenon of self-reference at every level, in Gödel's incompleteness proofs, in the recursive structures of Bach's musical compositions, in the drawings of Escher, in which hands draw each other and staircases loop back to their own beginnings. The quine fit naturally into this territory because it demonstrated that self-reference was not merely a logical or artistic trick, but a rigorous, runnable, verifiable property of computation. The bootstrap structure of the quine is clean. The program produces the text of itself. The text it produces is the program. Neither came first. There is no version of the program that arrived without the program already existing to have written it. If one asks where the first version came from, the answer the structure itself provides is that the question may be framed incorrectly. The quine does not have a first version in the way that a letter has a first draft. It is, in itself, a thing that refers only to itself, without thereby becoming incomplete or incorrect or inconsistent. It runs, it produces output. The output is itself. Hofstadter's book placed the quine alongside Gödel's incompleteness theorems and alongside the paradox of self-referential sentences, the family of statements that assert things about themselves in ways that seem to spiral back without resolution. The book ran to nearly 800 pages and became one of the more widely read works of popular science and philosophy published in the 20th century, which is notable for a book that spends a considerable portion of its length on formal logic and the structure of recursive systems. Hofstadter was not trying to alarm his readers. He was trying to show them that self-reference, which most people encounter as a mild linguistic puzzle, is a deep feature of formal systems, of cognition, and apparently of physics. The distance between Heinlein's notebook and Hofstadter's quine is not as large as it might initially appear. Both are information structures that exist within a loop. Both resist the question of where they began. The notebook's contents were never written by anyone. The quine source code was never authored by a prior program. In both cases, the loop closes on itself, and the question of the origin point is answered, not by identifying the origin, but by discovering that the structure does not require one. The physical objects that these ideas emerged from are worth dwelling on for a moment. The October 1941 issue of Astounding Science Fiction has the weight and feel of any pulp magazine of the period. Lighter than it looks, slightly rough to the touch, the ink on the cover slightly shinier than the paper beneath it. The name Anson MacDonald, printed beneath the story's title, is a small piece of quiet fiction within the fiction, a borrowed name that Heinlein used several times and then set aside. The story inside is written in the plain, workmanlike prose of the pulp era, more interested in plot than in style, and yet the logical structure at its center is as precise as anything in the physics papers it preceded. The reviews of modern physics papers from 1945 and 1949 have a different texture. They are printed in double-column journal format on slightly better paper, the equations set in a typeface that was standard for scientific publishing of the period, the density of the notation varying with the difficulty of what is being conveyed. The Feynman-Wheeler paper on absorber theory runs to several pages and contains the full mathematical treatment of the backward wave, the equations sitting in their column with the patience of things that do not require the reader to be alarmed by them. The Gödel paper on rotating universes is shorter and in some respects more remarkable for its compression. The key result presented without fanfare, the implications noted and left for others to develop. What connects these objects? The magazine, the physics papers, the computer science textbook is not a theme imposed from outside, but a structure that kept reappearing as researchers in different fields followed different lines of inquiry to their natural ends. The loop without an origin is not a literary invention that physicists later found they could describe mathematically. It appeared in the mathematics before and alongside the literary version. Gödel was not reading Heinlein. Wheeler was not thinking about notebooks. The bootstrap structure emerged from the formal study of electrodynamics and the formal study of space-time for reasons internal to those subjects. The Quine arrived by yet another path, from the study of what computation can and cannot do, from the attempt to understand the theoretical limits of formal systems that had been initiated in part by Gödel's incompleteness work of the 1930s. The word bootstrap in the original sense refers to the loops of leather stitched to the upper back of a boot to allow the wearer to pull it on. The phrase pulling oneself up by one's own bootstraps captures the original paradox. The motion requires a surface to push against, and the surface is the thing the motion is supposed to produce. The computer science usage arrived when early computing systems needed to initialize themselves, to run a small program to load the larger program that would actually run. And the question of what ran the small program first had a certain recursive quality to it. What Heinlein did, whether by design or by following the narrative logic of the structure he was exploring, was to give the bootstrap its most vivid everyday form, a piece of paper with writing on it, passing from one moment to another in a loop so complete that the writing was always already there. The notebook and By His Bootstraps is not the product of any particular act of authorship. It is the product of its own continued existence. This is a strange thing to hold in mind. It is also not, given what the physics and mathematics of the same period were producing, an isolated strangeness. The structure was appearing in multiple places at once. The particular pleasure of the bootstrap paradox, approached in the way a good puzzle box is approached, is that it does not break anything. The notebook does not violate conservation of energy. The Quine does not crash the machine that runs it. The absorber theory did not produce contradictions, only consequences. Gödel's rotating universe was mathematically consistent, a valid solution to valid equations. Nothing in any of these cases blew up. The loop closed cleanly, and everything inside the loop remained coherent, and the only thing that turned out to be missing was a starting point. Most structures we encounter in the world have starting points. A sentence has a first word. A building has a foundation that was laid before the walls were raised. A conversation has an opening exchange. The assumption that things begin is so ordinary, so close to the texture of daily experience, that it functions less like a belief and more like a background condition, something the mind supplies automatically to every sequence of events it observes. The bootstrap structure does not argue against this assumption. It simply produces, in specific and well-documented cases, a clean exception to it. The exception is not violent, it does not announce itself. It arrives in the mathematics of electrodynamics, in the geometry of a rotating universe, in the output of a program running on a terminal screen in a quiet room. It arrives in the plot of a story published in a pulp magazine in 1941 under a borrowed name. Each time it arrives, it is the same structure, something that exists because it exists, something that refers to itself as its own origin, something that closes without requiring a door to have been opened from outside. Hofstadter spent considerable energy in Gödel, Escher, Bach, arguing that this kind of structure was not merely a curiosity, but a fundamental feature of any sufficiently rich formal system, and possibly of thought itself. The argument is developed slowly across many chapters, through a series of dialogues between imaginary characters, and a set of careful formal proofs. The conclusion, to the extent that a book of that kind arrives at a conclusion, is that self-reference is not a defect or a malfunction. It is what complex systems do when they become complex enough to describe themselves. The loop is not an error in the system. The loop is something the system produces when it reaches a certain level of organization. That argument, stated plainly, sounds more dramatic than it reads in context. In context, in the particular rhythm of Hofstadter's prose, it reads more like noticing than like announcing. The same quality appears in the physics papers, in the careful mathematical language that Feynman and Wheeler used to describe the backward wave, in the compressed notation that Gödel used to describe the closed time-like curves of his rotating universe. The scientists and logicians working on these problems were not making large claims about the nature of reality. They were following their equations to where the equations led, and noting, with appropriate precision, what they found when they got there. A terminal screen in a quiet room. The room is otherwise dark. The cursor blinks at the left margin, steady and unhurried. A Quine program has been executed, and it is printing itself out, line by line, in the order in which the lines appear in the source code that is also the output. The characters appear one at a time or in small groups, depending on the machine and the implementation. The text accumulates on the screen. When the program finishes, the text on the screen will be identical, character for character, to the program that produced it. There is no original version of that text anywhere in the record. The program was written at some point by some programmer, and that writing was a real act that happened in real time. But the program, once written, produces itself. The act of writing that first version sits outside the loop, upstream of it, a moment of authorship that the loop does not require and does not contain. The loop runs perfectly well without it. If one imagines the program running forward from the moment it was first written, passing through a long sequence of executions, each producing the next, one eventually arrives at a loop so established that the question of the original author begins to feel like a question about something that no longer touches the loop at all. The cursor blinks. The characters continue to appear. The text on the screen is the program. The program is the text on the screen. The room is quiet, and the question of where the first version of that text could possibly have come from rests there in the dark, not urgently, not with any particular demand, but with the specific quality of a question that has been posed precisely and left open deliberately, the way a good question always is. The screen glows in the dark room. The text accumulates. Somewhere in the gap between what the program does and where it originally came from, the Bootstrap paradox rests quietly, doing nothing more and nothing less than existing, which turns out, in this particular case, to be exactly enough. In Princeton, in 1949, There was a journal sitting on a library shelf. It was a copy of Reviews of Modern Physics, and if a person had pulled it from the shelf and opened it to the relevant page, they would have found a paper by Kurt Gödel describing a universe made of rotating dust. Not metaphorical dust, a uniform, slowly turning medium that filled all of space, and whose rotation, when fed into the equations Einstein had published 30 years earlier, produced something that most physicists had assumed those equations could not produce. The mathematics on the page was clean and formally correct. What it described was a universe in which every moment in time was in principle reachable from every other moment, not by traveling very fast or very far, but by following the geometry of space-time itself, which in Gödel's rotating universe curved around until it completed a closed path. Gödel had worked through the calculation with the kind of careful precision that characterized everything he produced. The paper was not a speculation or a thought experiment dressed in the language of proof. It was an exact solution, a specific set of values inserted into Einstein's field equations that satisfied them completely, and that described a universe whose structure permitted what physicists call a closed time-like curve. A traveler in such a universe, moving along one of those curves, would eventually return to the same point in space-time from which they had departed, including the same moment in time. Einstein read the paper. He found the mathematics impeccable. He said so in writing, in a response published in the same volume. What he found more difficult was the implication, which was that the equations he had spent decades refining did not on their own rule out time travel. The geometry he had described was permissive enough to contain Gödel's solution alongside all the others. The two men had offices near each other at the Institute for Advanced Study. By 1949, they had been colleagues there for more than a decade. Gödel's working method was unhurried and meticulous, and he had apparently spent some years on the calculation before presenting it. When he handed Einstein the paper, the thing he was handing him was a piece of mathematics that lived quietly inside the structure Einstein had built, waiting to be noticed. It was not a challenge to relativity. It was a consequence of it, sitting in the space the equations had always permitted, patient and formally exact. What Gödel's solution described, in its physical terms, was a universe turning uniformly in a single direction. In such a universe, the rotation of the matter creates a dragging effect on the local structure of space-time, and if that dragging is strong enough and uniform enough, it produces regions where the causal structure of space-time folds, a path that appears to be moving always forward in local time, always from the past toward the future, always in the direction a clock would tick, can, in a Gödel universe, curve around until it arrives at its own beginning. There is no point on the path where time runs backward. The traveler ages normally. The clocks tick normally. The loop closes because of the geometry of the space through which the traveler moves, not because anything about the traveler's experience is reversed or distorted. The universe Gödel described is one in which the concept of a universal past and a universal future simply does not exist. Every event is in some sense simultaneous with every other. The whole of time forms something closer to a shape than a line. In the decades after that paper, other physicists began examining the conditions under which space-time could develop similar structures, closed paths that permitted a traveler to return to their own past. Much of this work was theoretical, but it was precise theoretical work, carried out with the same tools that had produced verified predictions in quantum mechanics, general relativity, and electrodynamics. One of the people who worked carefully on these questions was Kip Thorne, a physicist at the California Institute of Technology, whose career had included serious productive contributions to the theory of gravitational waves, black holes, and the structure of spacetime at its most extreme. In 1988, Thorne and his colleague Michael Morris published a paper in the American Journal of Physics. The paper began, somewhat unusually, with a premise drawn from a request Thorne had received from a novelist. But the physics that followed from that premise was not informal or illustrative. Morris and Thorne worked through the mathematics of traversable wormholes with care, and what they found was specific and publishable. A traversable wormhole, in their treatment, was a tunnel through the geometry of spacetime connecting two separate regions. Unlike the wormholes that appeared in other solutions to Einstein's equations, the Morris-Thorne wormhole was stable enough, in principle, to permit passage in both directions without the traveler being destroyed. The two ends of the wormhole were called mouths, and in the spacetime around each mouth, time passed at the rate appropriate to its local conditions. What Morris and Thorne described next was a procedure. If one mouth of the wormhole were accelerated to a high fraction of the speed of light and then returned to rest, relativistic time dilation would cause that mouth to age more slowly than the mouth left behind. The two mouths would then exist at different points in time. A traveler entering the mouth that had been accelerated would emerge from the stationary mouth at a different time than they entered. If the time difference were large enough, and the traveler moved between the mouths in the right direction through ordinary space, the circuit could be completed before the traveler's own departure. Thorne and Morris described this as a machine for time travel to the past. They did not claim such a machine could be built. They did not claim the exotic matter required to hold the wormhole open could be produced in the quantities needed. What they claimed was that the structure was consistent with general relativity, that no known principle of physics ruled it out, and that it would produce, if realized, the physical conditions required for a causal loop. The paper generated responses from across the physics community, as intended. Thorne had hoped the question of whether physics ultimately prohibited closed time-like curves would be taken seriously as a physical question rather than dismissed as science fiction. The responses that came back included Stephen Hawking's chronology protection conjecture, proposed in 1992, which argued that quantum effects at the mouths of wormholes would generate enough radiation to destroy the wormhole before it could be used for time travel. But Hawking framed this as a conjecture, not a proof. The question of whether chronology protection holds in all quantum gravity regimes remains open. The wormhole sits in the equations, traversable in principle, and no closed proof has been produced that prevents it from being used. These structures, Gödel's rotating universe, the traversable wormhole, the closed time-like curve, shared a feature that made the Bootstrap paradox not merely a logical curiosity, but a physical one. If information could travel along a closed time-like curve, that information could arrive at a point in time before it departed. A message sent backward around the loop would exist at the moment of reception before it existed at the moment of composition. The information would be real, fully formed, and physically present, and its origin within the loop would be nowhere. The loop would contain a piece of information that came from itself, with no point in the circuit where the information was first created. This was not merely a storytelling problem. Physicists had to account for it. If the geometry of spacetime permitted closed paths, and if information could travel along them, the question of what happened to the self-consistency of physics was a genuine one. The physicist who addressed it most directly and most formally was David Deutsch at the University of Oxford, who in 1991 published a paper in Physical Review D titled Quantum Mechanics Near Closed Time-Like Lines. Deutsch's approach was to ask what quantum mechanics predicted for systems that could interact with a closed time-like curve. Classical treatments of the problem tended to produce paradoxes, the grandfather paradox being the well-known case, in which a traveler goes back and prevents their own journey, making the journey both necessary and impossible. But classical mechanics treats information as perfectly definite. A message is either sent or it is not. Deutsch's observation was that quantum mechanics does not treat information this way. Quantum states are described by density matrices, which encode not just definite values, but probability distributions over possible values. A quantum system does not have to be in one definite state or another. It can exist in a superposition or in a mixture, and both of those are encoded in the density matrix. What Deutsch showed was that for a quantum system interacting with a closed time-like curve, a self-consistent solution always existed, not just sometimes, not under special conditions, but always. The mathematics guaranteed it. For any interaction a traveler might have with the past, there was a quantum state, expressible as a density matrix, that reproduced itself after passing around the loop. The Bootstrap paradox, in which a piece of information has no origin because it travels from its future self to its past self indefinitely, was in Deutsch's framework not a paradox at all. It was a fixed point. The density matrix that described the looping information was the one that satisfied the condition of being identical before and after the interaction with the closed time-like curve, and Deutsch's mathematics guaranteed that such a fixed point existed for every possible interaction. The fixed point solution was not physically intuitive in the way that a wormhole diagram is physically intuitive. It was a matrix equation printed in a column of a journal that most people would never open, but what it meant was precise. It meant that the bootstrap structure, the loop in which something comes from itself, could be formally accommodated by quantum mechanics without contradiction. The loop did not break physics. It satisfied physics as a fixed point satisfies an equation by being exactly what it needs to be in order for the whole structure to hold together. In the same years that Deutsch was working through the quantum mechanics of closed time-like curves, another line of research was probing the causal structure of quantum mechanics from a different angle. This work was not concerned with wormholes or rotating universes. It was concerned with something that happened in laboratories, between particles separated by nothing more dramatic than a few meters of optical bench and fiber cable. The phenomenon was quantum entanglement, and the specific question being pursued was whether the correlations entanglement produced could be explained without referring to anything that behaved like a signal traveling between the particles. The experiments Alain Aspect and his team conducted at the Institut d'Optique in Orsay in the early 1980s had provided very clean evidence that the answer was no. The correlations between entangled particles were stronger than any model based on locally held, pre-existing information could produce. Whatever connected the particles was not a message traveling between them in the ordinary sense. The connection was non-local. It was not, as far as anyone could tell, mediated by anything moving through the space between the particles at any speed at all. This did not immediately produce a causal loop, and physicists were careful not to claim that it did. The correlations in Aspect's experiments could not be used to send a message faster than light in a way that would allow the construction of a signaling channel. But the structure of the correlations, the way the outcomes at one detector were related to outcomes at the other in ways that defied local explanation, continued to raise questions about the direction of causation. If neither particle determined its own outcome independently, and if no signal passed between them, then the question of what caused each outcome to be what it was remained genuinely open. This openness was part of what motivated John Archibald Wheeler in his later years to articulate what he called the participatory universe. Wheeler had been one of the great figures of 20th century physics, a collaborator of Niels Bohr, the physicist who had formalized the concept of the black hole, the man who had coined the term wormhole. By the 1980s, he was thinking carefully about what quantum mechanics implied for the nature of reality at the largest scale, and what he arrived at was a vision in which observation was not merely a way of reading off pre-existing values, but a genuine participant in the constitution of physical reality. Wheeler presented the participatory universe concept formally in a 1983 paper he titled Law Without Law. The central claim was that the laws of physics were not written into the universe from the beginning, waiting to be discovered, but were in some sense brought into being by the universe observing itself. Wheeler drew a diagram of the universe as a loop of wire whose far end curves back to form an eye looking at its own near end. The universe in Wheeler's picture was self-referential in a deep and literal sense. The presence of observers who could ask questions and record answers was not incidental to the universe's history, but integral to it. The retroactive element of this picture was specific and documented. Wheeler described what he called delayed choice experiments, in which the decision about what measurement to perform on a photon was made after the photon had already begun its journey. Under quantum mechanics, what was decided at the moment of measurement appeared to reach backward in time to influence the photon's behavior at the point of emission. The photon seemed to have been, in some sense, different kinds of thing at its origin, depending on what question was asked of it at its destination. Wheeler's interpretation of this was that the concept of a definite photon with a definite history independent of observation was not sustainable. The photon's past, in some sense, was settled by its future. Wheeler did not present this as a paradox or as a violation of any physical law. He presented it as a consequence, carefully drawn, of what quantum mechanics said about the relationship between observation and reality. The picture was strange, but its strangeness came from taking quantum mechanics seriously rather than from departing from it. The delayed choice experiment had been a thought experiment in Wheeler's 1978 presentation of it, but it was later run as a real experiment by multiple groups and confirmed that the quantum mechanical predictions held. What was decided late appeared to determine what had happened early. What made Wheeler's picture relevant to the Bootstrap structure was its implication about origins. If the properties of a physical system can be retroactively determined by an observation that has not yet been made, then the causal chain running from origin to outcome is not the only chain that matters. There is also a chain running from the future toward the past, settling things that could not be settled in advance. The information in the system, the record of what the photon did, does not have a single fixed point of origin at the moment of emission. It comes into existence as something definite only when the observation closes the loop. This was not a loop in the same sense as Gödel's closed time-like curves, or the Bootstrap information loops of science fiction, but it shared a structural feature with them. The causal story, told forward in time from emission to detection, was incomplete. Something came back from the measurement end to complete it. The photon's behavior was not fully determined by its past alone. Its future reached back into its past and contributed something to what that past was. The University of Queensland experiments published in Nature Physics in 2020, led by Jacques Romero and Fabio Costa, pressed this structure further. What Romero and Costa's team demonstrated was that quantum operations could be performed in a superposition of causal orders. In ordinary physics, if operation A and operation B are performed on a system, either A happens before B or B happens before A. The causal order is fixed. What the Queensland experiments showed was that a quantum switch could place the control system of the experiment itself into a superposition so that the order in which a photon encountered two operations was not determined until after the measurement was complete. This was not a demonstration that A caused B and also that B caused A. It was a demonstration that the causal order between A and B could be a quantum variable, something that did not have a definite value until the measurement resolved it. The causal structure of the experiment was in superposition in the same way that a particle's spin is in superposition before it is measured. The experiment produced results that could not be reproduced by any model in which the causal order was fixed in advance. Causal order in the quantum domain was not always a primitive, settled feature of the world. Costa and his colleagues had been working on the theoretical framework for this kind of experiment for some years before the 2020 results. The theoretical structure was called an indefinite causal order, and its formal development had required extending the ordinary quantum formalism to include the causal order itself as a quantum variable. What the formalism produced was a set of predictions that were experimentally testable, and the 2020 experiment tested them. The results were consistent with the theoretical predictions for indefinite causal order and inconsistent with any classical causal model. The implication was not that cause and effect were abolished or that physics had become arbitrary. It was something more specific and in a certain way more interesting. In the quantum domain, at the scale of individual photons, in carefully constructed optical experiments, the question of which operation came first was not always a question with a definite answer prior to measurement. The causal structure of the universe, at that scale, participated in the quantum superposition principle that governed everything else. It was subject to the same rules as spin and position and momentum. It was a variable, not a fixed background. Sitting alongside all of this, in the literature of physics was the Wheeler-Feynman absorber theory, which had proposed something similarly retroactive about electromagnetic radiation decades earlier. In the original formulation, which Richard Feynman and John Archibald Wheeler had worked out together and published in Reviews of Modern Physics in 1945, a charge emitting electromagnetic radiation did so not unilaterally, but through a handshake between a wave propagating forward in time and a wave propagating backward in time from the absorbers in the future. The radiation was the result of both waves together. The charge at the moment of emission was responding, in some sense, to the absorbers it had not yet reached. Feynman later moved away from the absorber theory and toward the path integral formulation of quantum mechanics, which became one of the foundational frameworks of modern physics. But the absorber theory remained in the literature as a formally consistent alternative to the standard picture of radiation, one in which backward in time influence was built into the basic mechanism of how light was emitted. The physical picture it described was not a loop in the Bootstrap sense, but it shared with the Bootstrap the property of requiring that causation flow in both directions along the time axis simultaneously. The emission was caused, in part, by what had not yet happened. These various frameworks, Gödel's solution, the traversable wormhole, Deutsch's fixed-point theorem, Wheeler's delayed choice, the indefinite causal order, the absorber theory, did not compose a single unified theory of causal loops. They came from different research programs, addressed different questions, and used different mathematical tools. But across all of them, the same structural feature appeared: the assumption that causation always moved cleanly forward, from a settled past to an open future, and that every event had an origin that preceded it, was not a feature that the mathematics uniformly preserved. The equations, in each of these cases, permitted or required something more complicated. They allowed the future to contribute to the past. They allowed loops to close without a beginning. They allowed fixed points to exist where what was produced was identical to what produced it, with no external input required to start the cycle. Deutsch's fixed point result, in particular, had a quality that was worth sitting with for a moment. The density matrix he described was not an approximation or a special case. It was a mathematical guarantee. Given any quantum system interacting with a closed time-like curve, the space of density matrices for that system always contained at least one fixed point, a state that, after passing through the interaction the loop imposed, returned to itself unchanged. The loop closed. The state reproduced itself, and the mathematical guarantee of that reproduction meant that a bootstrap structure, a piece of information that came from itself, was not a violation of quantum mechanics but a consequence of it. The mathematics did not merely permit the loop. The mathematics required that the loop, if it existed, contain at least one consistent state. The loop was always somewhere in the space of solutions, complete. The paper itself, in Physical Review D, is a narrow column of dense notation on printed pages that have, in most of the world's physics libraries, yellowed only a little at the edges. The journal is shelved alongside the others from that year in the section devoted to gravitation, particles, and fields. The fixed point theorem occupies a modest portion of the paper, stated as a result and followed by its proof. The proof is not long. What it establishes, in the space of a few careful steps, is that the bootstrap structure is mathematically well posed, that the loop contains within itself everything required for its own continuation, and that no input from outside the loop is needed to keep it running. The information it carries came from itself. The loop closes without a seam. This was, in the end, not a disturbing result. It was a tidy one. Physics had found, through several independent routes and with several different formalisms, that the structure of a self-sustaining loop, something that originated from itself and required no prior cause, was not prohibited. It was not the default structure of physical causation. It was a special case, arising under specific geometric or quantum conditions, but within those conditions, it was stable, consistent, and formally guaranteed. The mathematics had made room for it, quietly and without drama, the way mathematics often makes room for things that seem implausible until the calculation is complete. The equations sat in their journals on those library shelves. The result in Deutsch's paper printed in the column beside his proof. The loop it described closed and self-consistent, and within its own mathematical world, complete. Nothing in that world demanded a starting point. Nothing in the structure required that the information have come from anywhere other than itself. The loop ran, and the density matrix reproduced, and the mathematics held, all of it fitting together with the precise and unhurried fit of something that had always been true, waiting only for someone to write it down. In the autumn of 1900, off the small Greek island of Antikythera, a group of sponge divers came up from depth, carrying something they did not recognize. The water there runs cold and deep, and the divers worked the seafloor in shifts, pulling sponges from the rocky shelves at the edge of an ancient shipping lane. What one of them brought to the surface that season was a piece of corroded bronze, green and gray, and heavy in the hand, the kind of weight that suggests solid metal underneath the crust of 2,000 years. The diver held it in both hands in the boat. He could not have known what it was. No one alive at that moment could have known, because the object in his hands had not been seen or described or cataloged by any living person, and the knowledge required to recognize it would take another century to fully assemble. The fragment was part of a device recovered over the following months by Greek Navy divers from the wreck of a Roman-era cargo ship that had gone down sometime around the 1st century before the Common Era. The full recovery of the device took decades of careful work. What emerged, piece by corroded piece, was a mechanism of extraordinary complexity. Bronze gears of different sizes, a series of dials and pointers, and interlocking rings, whose teeth meshed with a precision that required advanced metalworking to produce. Researchers named it the Antikythera mechanism, after the island where it was found, and placed its manufacture somewhere between 150 and 100 BCE. The object now rests in the National Archaeological Museum in Athens, and the full picture of what it does emerged only in the 21st century, when X-ray tomography finally allowed researchers to read its interior geometry without dismantling it further. What the X-ray imaging revealed was a bronze-geared calculator designed to track the motions of the sun and moon, predict solar and lunar eclipses, model the irregular speed of the moon as it moves through its elliptical orbit, and display a 4-year cycle of athletic games corresponding to a calendar in use across the ancient Greek world. The mechanism's front face carried a display of the Egyptian calendar and the Greek zodiac. Its back face tracked the metonic cycle of 19 years, over which the phases of the moon returned to the same calendar dates, and the Saros cycle used to predict eclipses. The differential gear, a mechanical component generally thought to have been invented in the 16th century CE, was present inside it, interlocking two separate computational systems into a single coordinated output. The gear trains required to produce this behavior involved no fewer than 37 individual gears working in coordination. No other device of comparable mechanical complexity is known from the ancient world. The archaeological record contains no bronze gears, no gear trains, no fragmentary evidence of the workshop tradition that would have produced such things over the generations leading up to its manufacture. There are written descriptions of other astronomical instruments from roughly the same period, armillary spheres, sundials, water clocks, but none of those required the kind of interlocking gear mathematics that the Antikythera mechanism embodies. From the perspective of what survives in the record, the mechanism appears without antecedents. It is not that the path toward it cannot be imagined. It is that the path, if it existed, left nothing behind. The corroded bronze under X-ray light shows the internal arrangement of gears and spindles that researchers spent more than a century learning to read. The surrounding seafloor silt that held it for 2,000 years has been replaced by a glass case, and the object rests there in low light, its complexity evident even in its fragmentary state, the missing pieces having been lost to the sea or to the decay of things held too long in salt water. What the mechanism does, the researchers now understand reasonably well. Where the knowledge required to build it came from, and where it went afterward, the record does not say. Some objects are puzzling because they are unique. The Antikythera mechanism is among the most studied artifacts in the history of technology, and its study has produced a detailed and carefully verified account of what it could do. The puzzle is not in the mechanism's function. The puzzle is in the gap before it, the absence of any documented path from simpler things to this particular thing, sitting on the seafloor in a wrecked cargo ship already complete. In 1938, a German archaeologist named Wilhelm König was working at a site near the town of Rabu, southeast of Baghdad in what is now Iraq, when he encountered a set of clay jars that had been in storage at the Baghdad Museum. The jars were unremarkable in appearance, the kind of unglazed terracotta vessel common across the Parthian period, which ran from roughly 250 BCE to 224 CE. Kutreshtik examined them carefully. Inside each jar was a copper cylinder, and inside the copper cylinder was an iron rod, and the iron rod was held in place by an asphalt stopper at the mouth of the jar. Koenig recognized that this arrangement, a copper cylinder, an iron rod, and an electrolyte solution, was the basic structure of an electrochemical cell. He published his interpretation the following year. Subsequent researchers replicated the construction using Parthian-era materials and techniques. Replica jars of the same design, filled with grape juice or vinegar, produced measurable voltages. The figure most consistently reported in these experiments is approximately 1 volts, a modest but genuine electrical current. The replicas worked. The function appeared to be electrochemical. No Parthian text describes the construction of such a device, and no Parthian written record mentions electrochemical processes, electrical current, or any application that would require a steady low-voltage source. The jars were found near a Parthian settlement, and their construction is consistent with Parthian craft traditions in terracotta and metalwork. What they were made for, no one has determined. Koenig proposed they may have been used for electroplating, depositing a thin layer of gold or silver onto a metal surface by running current through a solution containing dissolved metal salts. This is a technically plausible application, and electroplated objects from the ancient Near East have been found, though none that can be definitively linked to an electrochemical process, rather than to the gilding and silvering techniques that ancient craftsmen demonstrably used without batteries. Others have suggested the jars may have had a ritual purpose, perhaps producing a mild tingling sensation in objects held by temple visitors, which would require only that the device worked, and not that anyone understood why it worked. None of these proposals has been confirmed by documentary evidence. The jar's purpose remains genuinely open. What stays in the record is this: a device that produces electricity, found in a context where electricity is not documented as a known phenomenon, made by hands that left no account of what they were building. The clay is old, and the copper and iron are shaped with evident intention. The configuration is not accidental. The components fit together in a way that works. The working is what makes the object interesting, and the absence of any written context around the working is what makes it difficult to place. Koenig found the jars in a museum storage room, examined them, and recognized what the combination of materials meant to someone who understood electrochemistry. Whether the person who assembled them recognized anything similar is a question the record offers no way to answer. The replica jars sit on laboratory benches in photographs that appeared in various journals and popular accounts throughout the second half of the 20th century. In those photographs, a small wire runs from the copper cylinder to a voltmeter, and the needle deflects. The deflection is small but consistent. The jar on the bench is doing what Koenig said it would do, and has been doing it, quietly, in various forms, for roughly 2,000 years. Some years before Koenig was examining the Baghdad jars, a different kind of document was making its way through the collections of early book dealers in Europe. In 1912, a Polish-American antiquarian book dealer named Wilfrid Voynich purchased a manuscript from the Jesuit library at Villa Mondragone in Italy. The manuscript was large, over 200 vellum pages, and entirely unlike anything in Voynich's considerable experience with old documents. Its text was written in an alphabet that resembled no known script. Its illustrations showed plants that resembled no identified species, astronomical diagrams of uncertain meaning, small figures of women bathing in pools connected by elaborate pipe systems, and zodiac-related imagery drawn in a style distinct from the European astrological tradition. Voynich recognized that he had found something genuinely without obvious parallel. He spent the rest of his life trying to have it deciphered, without success. The manuscript passed through several collections after Voynich's death and was eventually donated to Yale University, where it is held at the Beinecke Rare Book and Manuscript Library. In 2009, the University of Arizona conducted radiocarbon dating of the vellum and returned a date range of 1404 to 1438 CE. The date placed the manuscript firmly in the early 15th century, during the European late medieval period, when manuscript production was well documented and scribal traditions were well understood. The script in the Voynich manuscript does not match any documented scribal tradition from that period or from any other. The text has been analyzed by professional cryptographers, linguistic statisticians, machine learning systems, and generations of amateur enthusiasts. What every serious statistical analysis has confirmed is that the text behaves like language. The letter frequency distribution, the pattern of word lengths, the way certain combinations of characters appear in positions that would be consistent with grammatical structure. All of this is consistent with a natural written language, rather than with random symbol generation or simple substitution cipher. A 2019 analysis using a neural network trained on multiple natural languages confirmed the statistical signature of natural language structure in the text. The text behaves like language. No one has read it. The manuscript's botanical illustrations show plants with leaves, roots, and stems, drawn with evident care, in a style that suggests the artist was depicting something they had seen, or a tradition they had been trained in. The plants do not match any identified species in European, Near Eastern, or Central Asian botanical traditions. The roots of several plants are drawn curling into pools of blue liquid, in a way that has no standard parallel in European herbals of the period. The astronomical section contains circular diagrams with labels that may be star names written in the unidentified script surrounding arrangements of small figures. The cosmological section shows a series of circular charts whose meaning has not been agreed upon by any two researchers working independently. No companion document has been found. No other manuscript uses the same alphabet. No cipher key has been located in any archive. The manuscript has been in continuous institutional custody since at least the 17th century, when it appears in the correspondence of a Bohemian scholar named Georg Barisch, who described it as a riddle that had already frustrated him for many years. Before Barisch, the trail goes quiet. The manuscript's origins, its author, its purpose, and its language remain unresolved. It sits in its case in the Beinecke Library, and the text continues to flow across its pages in a script that statistical analysis confirms behaves like language, but that no living person reads. The botanical page most often reproduced in accounts of the manuscript shows a plant with broad leaves and a root system that disappears into a pool of the same blue ink used elsewhere in the illustrations. The text beside it runs in lines of even length, left justified, with occasional longer and shorter lines that correspond to what might be paragraphs. The script is regular and practiced. Whoever wrote it knew how to write it. Whether they invented it, inherited it, or transcribed it from something older is not recorded anywhere that has been found. A fired clay disc sits in a case in the Heraklion Archaeological Museum on the island of Crete. It was found in 1908 by an Italian archaeologist named Luigi Pernier, during excavations of the Minoan Palace at Phaistos on the southern coast of Crete in a room thought to have served an archival function. The disc is approximately 16 centimeters in diameter and about a centimeter thick. It was made by pressing small carved stamps into the surface of the wet clay before firing, producing a spiral of impressed signs that runs from the outer edge toward the center on one side and from the outer edge toward the center on the other side. The firing hardened the clay and preserved the impressions. The disc has been in the record since 1908, dated to approximately 1700 BCE, and in that time it has told researchers a great deal about itself and almost nothing about what it says. The signs on the Phaistos disc number 241 tokens, arranged in groups, separated by incised lines, the groups running along the spiral in a sequence that may be read from the edge inward or from the center outward. The groups contain between 2 and 7 signs each. The signs themselves are 45 distinct shapes, each produced by a separate stamp, depicting recognizable objects: a human head, a hand, a fish, a bird, a bee, a plumed headdress, a ship, a walking figure, a cat, a horn, a house. The level of detail in the stamps suggests they were made by someone with experience in working at small scale with fine tools. The use of preformed stamps rather than hand-incised lines is a distinctly efficient approach for a text that was to be reproduced, which has led researchers to describe the Phaistos disc as possibly the earliest known use of a movable type or stamp-based writing technology. No other object anywhere in the world bears any of the 45 signs. The disc has been examined in relation to Linear A, the undeciphered Minoan script, and to Linear B, the Mycenaean Greek script that Michael Ventris deciphered in 1952. It shows no convincing relationship to either. It has been compared to other early Bronze Age writing systems from the Eastern Mediterranean and Anatolia. No relationship has been confirmed. Several researchers have proposed decipherments over the years, some claiming the text is a hymn, others a land survey, others a ritual sequence. None of these proposals has achieved scholarly consensus, largely because, with only 241 tokens and no bilingual key, the statistical evidence available for testing any proposed reading is too thin to produce a definitive result. What can be said with confidence is that the disc was made by someone who had already solved several significant technical and organizational problems. The stamps were carved with skill. The spiral layout was planned before the stamping began. The signs were grouped in a way consistent with word or phrase units. The disc was fired, which preserved it, and was found in a context suggesting it was intentionally stored. All of this points to an object made with purpose and care, in a tradition sophisticated enough to have developed a stamp-based approach to text production. The tradition left one object, nothing before it in the record, nothing after it. The disc rests in its case in the Heraklion Museum under low light. Visitors who come to see it often stand quietly for a while, following the spiral of signs with their eyes from the edge inward, or from the center outward, as if the direction of reading might itself resolve something. The signs are clear and regular. The stamps that produced them were pressed into the wet clay with even force. The spiral is orderly. The text runs all the way to the center of the disc, without interruption, completing itself. Whether anyone alive will ever read it is a question the disc has been posing, without urgency, since approximately 1700 BCE. Some nights, standing in front of it, a person might notice that there is something settled about the disc's quality of weighting. It is not incomplete in the way a damaged object is incomplete. Missing pieces that once existed. Everything that was ever on the disc is still on it. The incompleteness belongs to the reader. not the object. The Byzantine harbor of Constantinople in the summer of 674 CE was defended by something that the Arab fleet attacking it had not encountered before. The Arab forces had assembled a large naval force as part of a multi-year campaign against the Byzantine capital, and their ships were well armed and effectively commanded. The weapon that met them is described in Byzantine chronicles as a substance projected from tubes or siphons mounted on Byzantine ships, which burned on the surface of the water and could not be extinguished by the water it burned upon. The Arab fleet withdrew. The weapon was used again in subsequent engagements, including another major Arab naval assault on Constantinople in 717 CE, which it repelled with similar effectiveness. Byzantine commanders used it in naval engagements over the following centuries. Then, by the middle of the 12th century, the accounts stop. The formula was gone. Byzantine sources attribute the development of the weapon to a Syrian engineer named Callinicos, described as a refugee from the city of Heliopolis in present-day Lebanon, who arrived in Constantinople around 670 CE and brought the weapon's design with him. This attribution is the most complete account the historical record offers of where Greek fire came from. No document written by Callinicos survives, no source from before his reported arrival in Constantinople describes the weapon or its components. No Byzantine text written after the weapon's introduction fully describes how it was made. The formula was treated as a state secret, which explains the silence in the official record, but which also means that when the institutional chain of custody that held the knowledge broke down, as Byzantine institutions eventually did, under the pressures of war and political fragmentation, the knowledge ended with it. Historians and chemists have proposed various reconstructions of Greek fire's formula. The proposals include combinations of quicklime, petroleum, and various organic resins. Some accounts suggest it may have incorporated naphtha from the petroleum seeps of the Caucasus region, which the Byzantines had access to through their trade networks. None of these reconstructions has been verified against primary evidence, because primary evidence of the formula's composition does not exist. The accounts of what it did, burned on water, clung to surfaces, could be projected as a stream, are consistent with several different possible formulations, none of which can be selected over the others on current evidence. What is clear from Byzantine military history is that the weapon worked. Its effectiveness at repelling naval attacks on Constantinople is documented in multiple independent sources from the period. The Arab withdrawal from the harbor in 674 and again in 717 is recorded in both Byzantine and Arab chronicles, which is unusual for a piece of military history of this period. Most engagements are described only by one side. The weapon's effect on opposing navies was sufficiently documented that it continued to appear in accounts of Byzantine military capability for several centuries after its introduction. The knowledge of how to produce it was held by a small number of people at the center of the Byzantine state and passed from person to person or from person to document through a chain that eventually broke. A state secret held long enough becomes, in the end, a gap in the record. There is no surviving description of the moment the knowledge was lost, no account of a final holder dying without passing it on, no record of a document destroyed. The accounts simply stop mentioning it. The formula that Callinicos carried from Heliopolis to Constantinople, if he carried it at all, traveled through several centuries of Byzantine history and then left no trace of where it went. The harbor at night, with the burning substance moving across the surface of the water in the dark, appears in Byzantine military chronicles with the matter-of-fact quality of a description written by people for whom the site was familiar. The writers described the fire without much elaboration. They were writing for an audience that knew what it was. The audience that knew what it was is gone, and the instructions that made the thing it was are gone with them, and what remains is a series of accounts describing what it did, from which the thing that did it cannot quite be reconstructed. There is a particular quality shared by these objects and accounts. It is not mystery in the dramatic sense, not the hidden and deliberate withholding that makes for a certain kind of story. It is something quieter than that, and in some ways more interesting. The Antikythera mechanism's gears turn in their housing, demonstrating their function to any researcher with the instruments to read them, while the workshop tradition that produced them leaves no mark on the record. The Baghdad jars produce their small voltage in every properly assembled replica, the copper and iron doing what they have apparently always done, while the hands that first assembled them left no account of why. The Voynich manuscript's text flows in its regular practiced script, across page after page, statistically indistinguishable from language, while the language itself remains on the far side of every decipherment attempt. The Phaistos disk holds its spiral of stamped signs in the same configuration they were pressed into the clay more than 3,000 years ago, the stamps applied with consistent and deliberate force, the text running all the way to the center as if it intends to be read. What each of these objects has in common is not that they are broken or incomplete. They are, by any structural account, whole. The mechanism performs its calculations. The jars produce their current. The manuscript contains its full text. The disk holds all its signs. The incompleteness is in the record around them, in the absence of the context that would allow the thing to be placed, the tradition to be identified, the chain of knowledge to be traced backward to a point where it can be said to begin. Origins, in the historical record, are almost always reconstructed rather than directly observed. A craft tradition is visible in the similarity between one object and another, in the gradual accumulation of complexity over generations, in the slow refinement of technique documented across a sequence of finds. When a sequence ends before it reaches the oldest known example, when the oldest known example has no peers and no predecessors that have been found, the question of where it came from stays open. The archaeological record is deeply incomplete, which means that absence of evidence is not evidence of absence in any strict logical sense. The predecessors of the Antikythera mechanism may have existed and simply not survived, or not yet been found. This is a reasonable possibility. It is also the case that they have not been found, and that the mechanism itself sits in the record without company. There is something restful about this, considered from a certain distance. An object that cannot be placed at the end of a chain is not diminished by the difficulty of placing it. The gears of the Antikythera mechanism meshed precisely when they were new, modeling the sky above the Mediterranean in the last century before the Common Era. They were designed to do that. They did it. The question of where the knowledge for their design came from does not change what they did or what they were. The knowledge either came from somewhere in a chain that has not survived, or, in the purely theoretical frame of a causal loop, it arrived from no point of origin at all. Neither possibility is more comfortable than the other. Both are, in their way, equally open. The Phaistos disk, in its case, is about the size of a large hand. The spiral of signs is small enough that a person has to stand close to read it clearly. The stamps are evenly pressed. The clay is fired to a warm terracotta color. The signs depict things: a bird, a fish, a plumed head, a walking figure, that a person from the Bronze Age Mediterranean would have recognized immediately, though the language those signs encode remains outside the reach of anyone alive. It has waited in Crete, on the island of Crete, since roughly 1700 BCE, first in the palace archive where Pernier found it, and then in the museum case where it now rests. 3,000 years is a long time to wait for a reader. It is also in the scale of the questions the disk raises simply by existing, not particularly long. The text continues around the spiral, sign by sign, group by group, from the edge toward the center on both faces, the whole circuit of its meaning intact and continuous and still, for now, quietly its own. In a laboratory at the University of California, San Francisco, in 1983, a person sat in a chair and watched a dot move around a clock face. Electroencephalography leads had been attached to their scalp with a kind of conductive paste, each one positioned with care over the supplementary motor cortex, the region of the brain that has a role in the planning and initiation of voluntary movement. The clock face in front of them was not an ordinary clock. It had a single dot that moved around its edge once every 2.5 seconds, faster than a second hand, slow enough to be tracked. The person had been asked to flex their wrist whenever they felt like it, and to note the position of the dot at the moment they first became aware of wanting to move. That was the experiment. It seemed, at first description, like a reasonably simple thing to measure. Benjamin Libet, the neurophysiologist running the study, had been interested for years in the timing of conscious experience. The recordings his equipment produced showed a particular feature of brain activity that had been observed since the 1960s, a slow electrical buildup in the motor regions of the cortex that preceded voluntary movement. It was called the readiness potential, and it rose in a long, smooth slope before any observable muscle action. What Libet's design added to earlier work was the participant's own report, not just when the movement happened, but when the awareness of intending to move first arrived. The gap between those two marks turned out to be the interesting thing. On average, the readiness potential began approximately 550 milliseconds before participants reported becoming aware of any intention to move their wrist. More than half a second. The brain had already begun preparing the action before the person sitting in the chair knew they had decided to do anything. The electrical buildup that preceded the movement was not a response to a conscious decision. It was already underway, already rising toward the threshold that would trigger the wrist flex, while the experience of choosing was still ahead of it. By the time the person felt the intention arrive, the process that would become the movement had been in preparation for a period that in the brain's terms was not short at all. The finding was published in the journal Brain, and it has been discussed, replicated, contested, and extended across the decades since. The debates around it are genuine and ongoing, the interpretation of what the readiness potential actually tracks, and whether it represents a causal commitment or something more like a low-level readiness that could still be canceled, has not been fully settled. What remained consistent across the research, even as the methodology was refined, was the basic temporal structure. The preparation for movement preceded the awareness of intending to move. The story the person told about their own decision, that it came first, that the brain then carried it out, was at the level of measurable electrical activity, a story told slightly after the fact. There is a word for the experience of sitting in a quiet room, watching a clock, and trusting completely that the order of events is exactly as it appears. The word is ordinary. That experience of intentions arriving, of decisions being made, of the body following, is among the most familiar things a person knows. What Libet's work introduced into that familiarity was a small, calm question about the timing, not a challenge to the experience itself, but a look at the gap between when things begin in the tissue of the brain and when they arrive in the account that the person gives of their own day. The brain, it turns out, is not simply a record of what happens, it is something more like an editor. It receives a continuous stream of signals from the body and the world, processes them across multiple regions on slightly different timescales, and then delivers something smoother and more coherent than the raw material would have produced on its own. Part of that editing involves time, the experience of when things happen, when a sound arrived, when a touch was felt, when the choice was made, is not a direct readout of physical timing. It is a version of timing built by a brain that has reasons, most of them very good ones, for preferring coherence to accuracy. One demonstration of this comes from a perceptual phenomenon documented by Yarrow and colleagues in a paper published in the journal Current Biology in 2001. It involves the eyes, specifically what happens in the fraction of a second after the eyes make a rapid movement from one point to another. These rapid eye movements happen constantly throughout the day. When the eyes jump from one place to the next, vision is suppressed during the movement itself. The brain effectively shuts down the visual input while the eyes are in transit, because the resulting blur would be more confusing than helpful. The world does not go dark during these movements. The person does not notice the gap. The reason they do not notice it is that the brain does something to fill it in. What Yarrow and colleagues measured was what happens to the perception of time in the period just after the eyes land on a new target. Participants were asked to look at a clock and report how long the second hand appeared to pause on the number it had just moved to. The second hand in physical reality paused for exactly the interval set by the clock's mechanism, the same interval it always paused for. But participants reliably reported that the first position after an eye movement appeared to last slightly longer than it actually did. The second hand seemed to hang there to occupy its position for a moment more than a moment. The explanation is that the brain, having suppressed visual information during the eye movement, assigns the first thing it sees after the movement to the period just before the movement ended. It backdates the post-movement stimulus, using it to fill in the gap during which vision was offline. The result is that the first image the eyes land on after moving appears in the experience of the person looking to have already been there when the movement began. The brain has quietly rearranged the order of arrival so that the gap is invisible. The experience is seamless. The mechanics, when measured from outside, show a before and an after that do not match what the person inside experienced. This phenomenon has a formal name. It is called chronostasis, from the Greek for time and standing still. The name was introduced precisely because the most notable feature of the experience is not a distortion, but an apparent stilling, a moment that persists a little past its allotted time. The clock hand seems to wait. It is the brain, not the clock, that has produced the pause. What the brain is doing in these cases is not making errors in the ordinary sense of the word. The suppression of vision during eye movements is useful. The backdating that fills in the gap is useful. A visual system that delivered an honest record of its own dropouts, that went dark, then bright, then dark again every time the eyes moved, would be far harder to use than one that presents a smooth, continuous world, even at the cost of some temporal accuracy. The brain has, over a very long time, found solutions to the problem of making coherent experience from discontinuous input. Those solutions involve, among other things, some quiet adjustments to when things appear to have happened. The relationship between the brain's account of timing and actual physical timing is not a fixed or simple one. It varies with the type of signal, the distance from the sensory surface to the cortex, the degree of attention, and conditions of arousal. A touch felt during a state of alertness arrives in experience at a slightly different time relative to its physical onset than the same touch during drowsiness. The color of a moving object changes how quickly it is perceived to be moving. The loudness of a sound changes the apparent timing of a flash of light shown simultaneously with it. The world does not arrive all at once, synchronized at a single moment of reception. It arrives in pieces along different pathways at slightly different intervals, and the brain assembles those pieces into something that feels simultaneous, all of which means that the causal story the brain produces, this happened, and then because of that, this other thing happened, is constructed. It is built from pieces whose actual physical timing the brain has already adjusted, reordered in small ways, and smoothed into a narrative. The narrative is usually correct in its broad outline. The loud sound did precede the flinch. The decision did precede the action at the level of experience, even if the neural preparation preceded the decision. The story holds, but it is, nonetheless, a story. It is made, not simply recorded. One of the places where this becomes most visible is in a neurological condition first described at the end of the 19th century. Gabriel Anton, a neurologist working in the German-speaking tradition, documented a pattern of behavior following damage to the primary visual cortex that was, at the time he described it, without a fully satisfying explanation, the condition he observed, and which now carries the names Anton-Babinski syndrome, after Anton and the French neurologist Joseph Babinski, who elaborated the account, presented in patients who had lost functional vision following cortical injury and who were completely unaware of this loss. The patients could not see. Tests confirmed this reliably, but when asked about their vision, they described it as entirely normal. More than that, they described their current surroundings in detail. They spoke of the objects in the room, the color of the walls, the appearance of the people present. When those descriptions were checked against reality, they were wrong, not confused or approximate, simply wrong, as though the patient were describing a room from a stock of remembered rooms rather than the one they were in. The patients were not lying. They were not performing. They showed no distress, no sense of anything amiss. The descriptions arrived in the same tone as any ordinary observation. What the brain was doing in these cases was maintaining the experience of vision in the absence of visual input. The normal channels for that experience had been interrupted by the cortical damage, but the system that constructs and reports visual experience continued to operate, drawing on whatever materials it had available. Those materials were internal, memory, expectation, the accumulated sense of what rooms look like, what faces look like, what the world generally contains. The brain produced a visual experience and attributed it to the present moment, to the room, to the scene, directly in front of the patient. There was no signal from outside telling it the account was wrong. The experience was smooth and confident and entirely self-generated. Anton published this description in 1899, and the account raised questions that the neuroscience of the time could not fully address. The mechanism by which the brain maintains and confabulates experience under these conditions has become considerably clearer in the decades since, but the basic observation remains as he left it. A brain that has lost its input can continue generating experience that is detailed, confident, verwarming, and entirely present tense, with no awareness of the gap between the generated account and whatever is actually there. The brain, under normal circumstances, is doing something structurally similar in a quieter register. The visual world is not delivered continuously and uniformly. There is a region at the center of each eye where the optic nerve exits the retina, producing a gap in the visual field, a place where no photoreceptors exist and no light is detected. The brain fills this region in seamlessly with whatever pattern surrounds it. Most people spend their entire lives without noticing this gap because the brain has made sure there is nothing to notice. The blind spot is not experienced as a whole, it is experienced as more of the scene. The filling in, the backdating, the readiness potential that rises before the decision it seems to proceed. These are not isolated anomalies. They are instances of a general feature of how the brain constructs experience. The brain is a forward-looking system. It builds predictions and tests them against incoming data, updating where necessary, filling in where data is absent or delayed. This is efficient. It is, in most situations, highly accurate. It is also, at the level of detailed timing, a system that has already committed to a version of events before all the evidence has arrived, and that sometimes commits to a version that the arriving evidence does not fully support. In the mid-20th century, the neurologist Roger Sperry had been working on a surgical intervention for severe epilepsy in which the corpus callosum, the large bundle of nerve fibers connecting the brain's two hemispheres, was cut to prevent seizures from spreading from one side to the other. The patients who underwent this procedure and who were subsequently studied in depth came to be known as split brain patients. Sperry received the Nobel Prize in Physiology or Medicine in 1981 for this work, and for what it revealed about the distinct functional specializations of the two hemispheres. Michael Gazzaniga, who collaborated with Sperry and extended the research considerably, documented a pattern of behavior in split-brain patients that is among the more striking findings in the history of neuropsychology. Because the corpus callosum had been cut, information delivered to one hemisphere did not reach the other. The left hemisphere controlled speech in most of the patients studied. The right hemisphere received signals from the left visual field and controlled the left hand by presenting a word or image only to the left visual field, so that only the right hemisphere received it, and then watching what the patient did with their left hand. Gazzaniga and Sperry could initiate actions in the right hemisphere without the left hemisphere having any knowledge of what had caused them. The left hemisphere, faced with an action it had not initiated and whose cause it could not access, did not respond by saying it didn't know. It explained, fluently, confidently, immediately. A patient whose right hemisphere had received the instruction to laugh, laughed, and then the left hemisphere described, in complete sentences, why. There was simply something funny about the situation. There was a particular absurdity in the question just asked. The explanation was different each time, always plausible, always delivered with the assurance of someone describing a straightforward observation. None of the explanations had any access to the actual cause. Gazzaniga eventually named this the interpreter, the left hemisphere's tendency to generate explanations for observed events, including events in the patient's own behavior, using whatever contextual information was available, regardless of whether it had any genuine access to the cause. The interpreter produces causal accounts. It produces them reliably and quickly and in a register that feels from the inside like accurate description rather than construction. The story has the texture of memory, of knowledge, of reporting. The story was made in the moment, from materials that had nothing to do with what actually happened. What the split brain studies revealed about the interpreter was something that had been true, in a quieter form, all along. The construction of causal accounts is not a response to gaps and damages. It is how the brain ordinarily operates. The left hemisphere, in a brain whose two halves are communicating normally, is still doing the work of building explanations for behavior, building them from the information it has access to, which is never the complete record of what is happening in the tissue below the level of conscious access. The causal stories feel accurate because the brain has no separate mechanism that checks them against a ground truth it cannot reach. They feel like reporting because reporting and constructing are in this domain the same operation. The rubber hand resting on a table in a university laboratory makes this visible in a different register. Matthew Butvinnik and Jonathan Cohen published their account of the rubber hand illusion in the journal Nature in 1998. The setup was simple. A participant sat at a table with one hand hidden from view behind a small screen, and a rubber hand placed visibly on the table in front of them at roughly the position where their real hand would be. An experimenter then used a small brush to stroke both the rubber hand and the hidden real hand simultaneously at the same location and in the same rhythm. After a short period, usually less than a minute, participants began to report feeling the sensation of touch in the rubber hand. The touch they felt in the rubber hand corresponded to the strokes being applied to it, not to the strokes applied to their actual hidden hand. More than that, neuroimaging of participants during the illusion showed activation in the premotor cortex, the region involved in the sense of body ownership, as though the brain had genuinely incorporated the rubber hand into its model of the participant's own body. When a researcher raised a pen as if to strike the rubber knuckles, participants flinched. What the brain had done was take two streams of information, the visual information showing a hand being touched, and the tactile information from the real hand being touched simultaneously, and resolve them into a single coherent account. The simplest account, given that the timing matched and the spatial positions roughly matched, was that both streams were reporting the same event. The brain had concluded, without any deliberate decision, that the rubber hand was the participant's own. The body had been, in a small and reversible way, redesigned by the information the brain had chosen to believe. The body map the brain maintains is not a static record of the physical self. It is a running inference, updated by the information available, subject to revision when the information suggests revision is warranted. Under ordinary circumstances, this process is invisible because it works correctly. The hand is where the brain says it is, and the world confirms this when the hand touches something. Under the controlled conditions of the rubber hand experiment, the inference can be steered toward a conclusion that does not match the physical facts. The brain follows the evidence where it leads, and in this case, the evidence leads somewhere that is not quite true. The infant who discovers that a reaching gesture produces a response in the world, that the hand, extended toward a colored object, makes the object swing on its cord, is building the same map from the same kind of data, except that in early life, all of it is being built for the first time. The body map, the causal map, the temporal map, the sense of which things precede which, the sense of which movements were decided and which simply happened. All of it is constructed across time from exactly the kind of evidence-based inference that the rubber hand experiment temporarily redirects. The eventual result is an experience of selfhood that feels immediate and direct, as though it were simply given. None of it was simply given. There is a way of describing all of this that sounds more troubling than it is. The brain does not record time. It produces a version of time. The brain does not receive the body. It constructs a body from signals. The brain does not observe decisions. It builds decisions from processes that are already underway. Each of those statements is accurate in the terms the research supports. The instinct to find them unsettling is also real. But the thing that is being described is not a failure. It is a system that has found, over an enormous span of time, a way to operate in a world where perfect information is never available, and where the cost of waiting for complete data before acting is too high. The readiness potential rises before the conscious intention because the brain is already doing the work before the announcement of the work arrives. The announcement still arrives. The intention is still real. The decision still shapes the outcome in the ways that matter. What the gap between them measures is not a defect but a feature of a system that has solved the problem of building coherent voluntary action from the complex and partially asynchronous signals of a living body. The backdating that produces chronostasis is the brain maintaining the experience of a continuous, uninterrupted world, which is the condition under which the brain can function most effectively. The solution it has found to the problem of eye movement suppression is not to present an honest account of the disruption, but to fill the disruption with something stable. From the point of view of navigating the world, this is the correct solution. From the point of view of someone asking precisely when the second hand moved, it is an artifact. The interpreter in the split-brain patient is applying, in an exaggerated and therefore visible form, exactly the mechanism the brain uses in every waking moment. The need to know why something happened, to place it in a causal sequence, to connect the action to a reason. This is not a feature that can be turned off without losing something essential. The interpreter constructs. Construction is not the same as invention. The accounts it produces are constrained by all the information the brain does have access to. They are not random. They are, in most cases, correct or close to correct. In the split-brain patient, they are wrong in a way that can be tested against a record the experimenter holds, and the left hemisphere cannot see. Libet's participant, watching the dot move around the clock face, will raise their wrist and note the position of the dot, and submit both the movement and the timestamp of the decision as their account of what happened. The account is genuine. The participant is not confused or performing. They are reporting the experience as it arrived to them, a moment of deciding, followed by a movement. That sequence is real in the sense that those are the events as experienced. The readiness potential on the recording trace, already rising before the experience of deciding began, adds something to the picture that the experience itself does not contain. Not a contradiction of the experience, but an additional layer, a longer history for the action than the person in the chair was aware of. The question of where the causal chain begins in the readiness potential, in whatever preceded the readiness potential, in the state of the whole brain and body, in the seconds before the wrist moved, does not resolve into a single, clean starting point. The wrist flexed because of a neural process that was underway before the person knew they had decided. The neural process was underway because of a prior state of the brain. The prior state of the brain was produced by everything that had happened to that brain before the moment of the experiment, the night's sleep, the breakfast, the years of accumulated experience that shaped which moments tend to produce a felt sense of readiness to move. The chain does not terminate at the conscious decision. The chain does not terminate anywhere that is easy to locate. The brain is not unusual in this respect. The brain is one instance of a more general feature of systems that operate over time, in which the causes of current states extend backward into histories that become increasingly difficult to trace and eventually become, for practical purposes, untraceable. But the brain is the particular instance that is closest to the experience of asking the question. It is inside the experience. It is the experience. And so, what the neuroscience of timing and causal attribution reveals is not something external and theoretical, but something structurally present in the act of wondering about it, in the fact that the wondering itself is a process whose beginning predates the moment it arrived in consciousness, assembled from materials the brain gathered before the question was consciously posed. Gazzaniga's split-brain patient, in a clinical room in the second half of the 20th century, laughed at something they had not consciously decided to find funny, and then, in clear and comfortable sentences, explained the laughter. The explanation was useful. It was fluent. It was constructed from everything the left hemisphere knew: the room, the researcher, the general register of the conversation, the usual kinds of things that are sometimes funny. It was entirely confident. The actual reason which had arrived from the other hemisphere along a pathway that was no longer connected was not available to it. The left hemisphere had what it had and made the best account it could. That account offered in good faith, built from all the available materials, coherent and calm, and a little wrong. It is, in its quiet way, a portrait of something the brain does in every waking moment, in the stories told about choices made, in the confident sense of having decided before the decision was finished, in the smooth and unbroken experience of a world that the brain has been quietly editing all along. The participant in Libet's laboratory will leave the experiment and go home and describe, if anyone asks, what it felt like to flex their wrist. They will say they decided to do it, and then they did it. This is a true account of their experience. The recording equipment will have produced something else, a longer story, the slow rise of electrical potential in the cortex before the announcement of the intention arrived. Both of those things are real. The gap between them does not need to be resolved to be interesting. It sits there, the same width as it always was, the same 550 milliseconds, while the brain, which produced it, continues its work of assembling the experience of the present from materials it has been collecting quietly and well before the present announced itself. That patient in Gazzaniga's laboratory, explaining their own laughter in complete and unhesitating sentences, not knowing and not needing to know that the reason they were laughing had arrived through a pathway that had been carefully and surgically closed. That patient spoke with the ease of someone who has never had to wonder whether their reasons are the actual reasons, because the brain they inhabit has always made sure the reasons and the account of the reasons feel like the same thing. They do. They generally are. And in the moments they are not, the account continues, warm and confident, telling the story of what happened and why, the story the brain has been writing, quietly, just slightly before the moment it appears to begin. A person moving south across the Antarctic ice sheet will eventually run out of south, not because a wall appears, or because the ground gives way, or because any marked boundary announces itself underfoot. The ice simply continues, curving gently away in all directions, and the question of where the southernmost point might be found turns out to be a question the geometry of a sphere does not permit. There is no edge to reach. The traveler keeps moving. The ice keeps curving. Stephen Hawking used this image to describe something that had occupied him for years, not Antarctica, but the beginning of the universe itself, and the specific question of what, if anything, came before it. The no-boundary proposal, published by James Hartle and Hawking in Physical Review D in 1983, described the universe using a wave function defined across all possible geometries of space. What the proposal suggested was that an imaginary time, a mathematical direction orthogonal to the ordinary flow of past and future, the universe has no boundary at all, no edge, no wall, no moment before which something else existed and from which the universe was launched. The question of what caused the Big Bang, framed this way, is not a question that has been asked correctly. It is like asking what lies south of the South Pole. The geometry simply does not provide a place for the answer to stand. This is not a statement about ignorance. It is a statement about shape. The traveler on the ice sheet is not failing to find the boundary because they have not looked hard enough. They are not finding it because the surface of a sphere does not contain one. Hawking returned to this image repeatedly in lectures and in writing, and there is something in it that repays slow attention, the way it turns an absence into a feature, the way it makes the lack of a beginning into a property of the universe's geometry, rather than a gap in knowledge. The ice continues. The curve is smooth. There is simply no point at which the ground ends. Imaginary time, in the mathematical sense Hartle and Hawking used it, is a direction obtained by multiplying ordinary time by the square root of -1. This does not refer to time that is pretend or hypothetical. It refers to a dimension in which the distinction between time and space dissolves, and in which the early universe can be described as a closed, smooth surface with no boundary, the way the surface of the earth has no boundary, no edge from which you might fall. In that description, the question of what came before the Big Bang is answered not with another event, and not with silence, but with the observation that the word before does not apply to a geometry without a seam. The Hartle-Hawking proposal remains one approach among several, and the peer-reviewed literature does not treat it as a settled account of how the universe began. What it offers within that literature is a mathematically coherent way of describing a universe that requires no cause outside itself. Whether the universe is in fact this way is a separate question, but the proposal shows that the absence of a beginning is not, on its own, a logical impossibility. It is a possibility the mathematics openly permits. The traveler searches for the edge and finds only more ice, and the ice, in this case, is the universe itself, curving quietly away in every direction, without ever arriving at its own boundary. Roger Penrose had a different picture in mind, though it shares something with Hawking's in the quality of its patience. Penrose developed conformal cyclic cosmology over many years, setting out its full framework in his 2010 book Cycles of Time, and in papers published in the journal General Relativity and Gravitation. The model proposes not a universe with no beginning, exactly, but a universe with no absolute beginning, an infinite succession of aeons, each one beginning in something like a Big Bang, and ending in a vast, nearly empty expanse, and each ending connecting seamlessly and without interruption to the next beginning. The mechanism that makes this possible involves conformal geometry, a branch of mathematics concerned not with size or distance, but with angles and shape. When two geometries are conformally equivalent, they have the same local structure, even if one is, in ordinary terms, enormously larger or smaller than the other. Penrose observed that the remote future of an aeon, a cold, empty, expanding space containing almost nothing but light, and the very early state of the next aeon, dense and hot and in rapid expansion, share a conformal structure. The two geometries, enormously different in scale, are in a precise mathematical sense the same. The ending and the beginning, described in these terms, are not separated by anything. They are the same surface described twice. In the remote future of one of Penrose's aeons, the picture is this: the last black holes have long since finished evaporating, the process taking on the order of 10 to the 100 years or more for the largest. The ordinary matter that once filled galaxies has long since decayed or dispersed. What remains moves at the speed of light, because only massless particles remain, and distances between those particles are almost unimaginably large. The universe is cold, nearly empty, and expanding. Time, in one sense of the word, has become almost meaningless in this environment, because there are no clocks, no physical processes rhythmic enough to measure intervals by. The expansion continues, the space grows, and then the conformal geometry of this vast, quiet expanse, connects to the conformal geometry of the next beginning, not with an explosion from a point, but with a smooth transformation. The size scale drops away from the description, and what is left is a geometry that is equivalent, in the relevant mathematical sense, to the earliest moments of a new aeon. A new expansion begins. Matter and energy reappear. The cycle continues. There is no seam between the end of one aeon and the beginning of the next that anyone inside either aeon could locate. The universe simply continues, its structure passing from one phase to the next with the same unhurried continuity as the Antarctic ice curving away underfoot. Penrose has noted and reported in papers as an area of ongoing investigation that this model makes certain predictions about the cosmic microwave background, the faint residual radiation left over from the early universe. Specifically, he and his collaborators have argued that gravitational wave events from the previous aeon involving collisions between black holes would leave faint rings of temperature variation in the microwave background. Whether those rings are present is a matter the literature has examined and continues to examine, and the finding remains contested. The model is not confirmed. What it is a carefully developed mathematical proposal in which a universe without an absolute beginning is a consistent description. Paul Steinhardt and Neil Turok proposed something with a different mechanism in a paper published in the journal Science in 2001. The Ekprysik universe model describes the universe not as a single aeon among many, but as one of two three-dimensional surfaces, branes, in the language of string theory, moving through a higher dimensional space. The Big Bang, in this description, is not an absolute beginning. It is a collision. The two branes drift slowly toward each other through the extra dimension between them, approach, collide, and the energy of that collision produces the hot, dense state that expands into the universe that can be observed. The branes then drift apart again, cool, and eventually begin slowly approaching each other once more. The distance between the two branes in the extra dimension at the moment before collision is very small, smaller than an atomic nucleus. From inside one of the branes, nothing about the approaching collision is directly visible. There is no signal traveling across the gap in the ordinary sense, because the ordinary senses available inside a brane do not extend into the extra dimension. The collision, when it comes, looks from inside the brane like the entire universe suddenly filling with heat and light and rapid expansion, which is, in every observable respect, what a Big Bang looks like. The brain does not know it has collided before. It does not know the process has happened an infinite number of times, but in the mathematics of the model, that infinite repetition is part of the structure. Steinhardt and Turok developed the ekpyrotic model partly in response to certain features of inflationary cosmology, and the relationship between these frameworks, what each predicts, and how those predictions might be distinguished by observation, remains an active area in the peer-reviewed literature. The model is one proposal among several serious ones. What it contributes to the picture being assembled here is a way of understanding the Big Bang, not as a wall at the edge of time, but as a moment in an ongoing process, one collision among an infinite series, the universe cycling through its phases as naturally as a wave moving through water, the water never beginning, the wave recurring, two branes moving through a higher dimensional space, drifting toward each other across a distance smaller than an atom over a span of hundreds of billions of years. The image has a particular quality to it, the slowness of the approach, the enormity of the scales involved, the fact that the collision produces everything observable about the universe and is itself invisible from within it. It is the kind of picture that changes the feeling of the word beginning without changing the facts of what is observed. The expansion is real. The early heat is real. The brain does not remember the collision before. The model simply asks whether the collision is the first. Fred Hoyle would have found the brain picture uncomfortable for reasons of its own, though he spent much of his career arguing against the need for an absolute beginning from a different direction entirely. In papers published in the monthly notices of the Royal Astronomical Society in 1948, Hoyle, Hermann Bondi, and Thomas Gold proposed the steady-state theory, a description of the universe in which expansion is continuous and real, but in which the average density of matter remains constant over time because new matter is continuously created throughout space. Not at a single point, not in a single event, but everywhere and always, at a rate low enough to be consistent with observation, roughly 1 hydrogen atom per cubic meter of space per billion years. In the steady-state universe, there is no Big Bang. There is no moment at which expansion began. The universe has been expanding forever, and it has always looked on large scales, roughly as it does now, because the matter created continuously fills in the spaces that expansion opens. The universe has no beginning and will have no end. It is not cycling. It is not bouncing. It simply continues in all directions and at all times without reference to a starting point. Hoyle used the phrase Big Bang in a BBC radio broadcast in 1949 in what appears to have been an expression of mild skepticism toward the competing theory, the theory describing a universe that began in a hot, dense state and has been expanding since. He did not expect the name to carry. It did. The term became standard, used by proponents and critics alike, eventually losing any connection to the tone in which it was first uttered. Hoyle continued to develop and defend the steady-state framework for decades, and the discovery of the cosmic microwave background radiation in 1965, which is more naturally explained by a hot early universe than by a steady state, moved the scientific consensus away from the steady-state model. But the model itself remains in the record. It is a carefully worked description of a universe that needs no beginning, proposed by serious researchers in a peer-reviewed journal, and the mathematics it contains did not stop being internally consistent when the consensus moved. There is something in all of these proposals, the no-boundary universe, the conformal cycles, the colliding brains, the steady state, that they share without having been designed to share it. Each of them describes a cosmos in which the question of what came before the beginning either dissolves into geometry or extends backward infinitely, or reveals the beginning to be a recurring event rather than a unique one. Each of them, in its own way, moves the wall. The wall had seemed fixed. It had seemed that the universe, whatever its nature, must at some point have started, that there was a moment on one side of which it did not exist, and a moment on the other side of which it did, and that between those two moments, something happened that required explanation. These frameworks do not all agree with each other about what replaces that picture, but they agree that the picture can be replaced, and they provide the mathematics to show it. The replacement is not a new mystery in the place of an old one. It is a change in the shape of the question, the way that searching for the South Pole eventually reveals that the specific thing being searched for does not exist as a wall, but only as a point on a curved surface that connects to everything else on the same surface. Abhay Ashtekar and his colleagues at Pennsylvania State University have been developing loop quantum cosmology in a series of papers published in Physical Review Letters and Physical Review D from 2001 onward. The framework applies the techniques of loop quantum gravity, a quantization of space-time itself, to cosmological models. What this produces, at the point where classical general relativity describes a singularity, is something different. In classical general relativity, tracing the universe backward in time leads to the Big Bang singularity, a point at which density and curvature become infinite, and the equations break down. The singularity is not a description of what happened. It is the place where the description stops. In loop quantum cosmology, the singularity is replaced. The quantization of spacetime introduces a minimum length scale, a granularity below which the geometry of space does not subdivide further. When the universe contracts to near that scale, the quantum geometry generates a repulsive pressure that the classical equations do not contain. The contraction slows. It stops. It reverses. What was a singularity in the classical description becomes, in the quantum description, a bounce, a moment at which a prior contracting universe transitions into the expanding universe that is observed. The expansion does not begin at the bounce. It resumes. The density at the quantum bounce in the framework Ashtekar and colleagues have developed is very large but finite. The numbers that appear in the calculations are specific, approximately 5.5 times 10 to the 96th kilograms per cubic meter. This is a density far beyond anything in ordinary experience, far beyond the interior of a neutron star, far beyond any condition that could be described or reproduced in a laboratory. But it is a finite number. The equations do not break down there. They pass through it. On one side of that moment, a universe is contracting. On the other side, a universe is expanding. The moment itself is not an edge. It is a transition. At the moment of the quantum bounce, the universe in loop quantum cosmology is smaller than a single atom. The entire observable universe, everything within the light horizon, all the galaxies and voids and the ancient light traveling through them, is at that moment compressed into a region smaller than an atomic nucleus, and then it begins to expand. Slowly at first, in the language of the model, the expansion accelerating as the conditions that drove inflation in the classical account emerge from the dynamics of the bounce. The universe grows. Time continues. The expansion that will eventually produce stars and galaxies and the faint hiss of the microwave background moves outward in all directions from a moment that is not a beginning. What lay before the bounce, in loop quantum cosmology, is a prior phase of the universe, contracting, growing denser, carrying within its structure the quantum correlations that will shape the expanding phase that follows. That prior contracting phase has its own prior phase. The chain does not terminate at a first moment. The model does not require one. The universe in this description extends backward in time indefinitely, passing through bounce after bounce, each contraction giving rise to a new expansion, each expansion eventually reversing into a new contraction. The structure is open in both directions. There is no first bounce. There is no last expansion. There is the process, continuing without a starting point, the same way the ice continues without a southern wall. None of these frameworks, Hartle-Hawking, conformal cyclic cosmology, ekpyrotic steady state, loop quantum cosmology, is confirmed by observation in a way that has closed the question. The peer-reviewed literature on early universe cosmology remains genuinely open. What these frameworks collectively establish is something more modest, and in its way more durable than any single confirmed theory, that a universe without an absolute beginning is not a logical impossibility, not a philosophical convenience, not a device of fiction. It is a mathematically coherent description that serious researchers have developed and continue to develop in peer-reviewed journals, and the tools of that work are the same tools used to describe things that are confirmed, the same equations, the same techniques of quantization, the same conformal geometry. The Bootstrap paradox, as it appears in physics and mathematics, asks how something can exist without ever having had an origin, how information can be passed backward through time without any version of it ever being composed for the first time, how a causal loop can close on itself without requiring a first cause to set it turning. The cosmological frameworks described here ask a version of the same question at the largest possible scale. How can a universe exist without a beginning? How can expansion resume rather than begin? How can the geometry of spacetime be shaped in such a way that the question of what came before has no surface to stand on? The answers these frameworks offer are not the same answers. They disagree about the mechanism, about the structure, about what the universe looked like before the moment we call the beginning. What they share is a direction of attention toward descriptions of the universe that do not require a wall, that find the absence of an absolute starting point to be a feature of the geometry rather than a failure of the explanation. The traveler on the ice keeps moving south. The ice keeps curving. The geometry of the sphere continues without providing the edge that was being searched for. And somewhere in that smooth continuation, in the unhurried curve of the surface away from the question, there is something that feels less like an absence and more like a kind of rest. The image of two brains drifting toward each other through a higher dimensional space, slowly and over spans of time that no instrument could measure, has a particular quality of patience to it. Hundreds of billions of years of approach across a distance smaller than any particle the collision will eventually produce. The collision arrives. The brain does not flinch. The heat and expansion fill the new universe. The brains move apart again, cooling, and begin their long, slow drift back toward each other across the extra dimension. If the model is correct, this has happened before, and before that, and before that without limit, without a first collision to begin the sequence. The universe that contains the stars and the light and the ancient expanding space was already, in some sense, not the first. It was not the last. Penrose's aeons have the same quality, held different. The geometry of a vast, cool, expanding emptiness connects without seam to the geometry of a dense, hot, rapidly expanding beginning. No moment of crossing exists for an observer inside either aeon to measure. The transition is not an event in time. It is a geometric relationship, the same surface, seen from two different scales, each one continuous with the other in the mathematics of conformal equivalence. In Penrose's picture, the universe is always in the middle of its own story. There is no first chapter. There is no chapter that precedes all others. There is the ongoing process, the aeons turning, the light of the last black holes fading in one aeon, and the light of the first stars appearing in the next, the geometry carrying both within itself, as naturally as a sphere carries its own surface. Hawking's traveler on the ice continues south, and the ice continues to curve, and the question of where the universe began dissolves not into an answer, but into the recognition that it was a question about an edge that the geometry does not contain. This is not the same as saying the universe has always existed in time. Exactly. Imaginary time is a mathematical direction, not a sequence of moments stretching backward into the past. What it is saying is closer to this. The universe does not require a cause outside itself, because the geometry in which it exists does not provide a location for such a cause to stand. The before is not missing. The before, in the Hartle-Hawking description, is simply not the kind of thing spacetime contains at that scale. The Ashtakar bounce happens at a density of approximately 5.5 times 10 to the 96th kilograms per cubic meter. The universe at that moment is smaller than an atom, and it is already moving. The contraction has already slowed. The quantum pressure is already reversing the direction of change. The universe that will expand into everything observable is already at that extraordinary density in the process of becoming that expansion. The bounce is not an event at which something new is created from nothing. It is a transition, the same matter, the same geometry, passing through a minimum scale and moving outward again. The way a breath held completely still for a moment contains within it the returning movement. The expansion does not begin, it resumes. In the quiet of that resumption, in the smooth continuation of geometry from one state to the next, the Bootstrap question and the cosmological question arrive at the same place. How can something exist without having started? The answer, or the shape of an answer, seems to be that start is a feature of certain geometries and not others, that it applies to processes that have a boundary, and that some processes, some geometries, some universes are not shaped in a way that provides one. The loop closes. The information exists without an original author. The universe expands without a first moment from which expansion began. The ice curves away from the question and continues. The last black holes in Penrose's prior aeon have been evaporating for longer than the current universe has existed, for longer, by many orders of magnitude. The process is slow, and it is governed by the same quantum mechanics that governs the smallest events in a laboratory. The black hole radiates, it loses mass, it grows smaller. Eventually, after a span of time that makes the current age of the universe look like a brief afternoon, it evaporates entirely. What is left is radiation, moving outward at the speed of light through a space that has grown so large that no two photons are likely to interact again for longer than the universe has existed. The eon ends not with a wall, but with a gradual diminishment, a settling, a cool and nearly empty space in which the last light travels without destination, and the conformal geometry of that space is the same as the conformal geometry of the next beginning. The surface connects, the new aeon begins. Somewhere in the new expansion, in the young hot plasma of a universe newly resuming, the conditions will eventually allow stars to form, and in those stars the heavier elements will be forged, and in the spaces between stars, the conditions will eventually allow planets, and on some of those planets, the conditions will eventually allow the question to be asked: what caused this? Where did it start? And the geometry of the answer, if Penrose's picture is correct, is that the question is being asked in the middle of a process that has no start to point to, a process that was turning long before the question existed and will continue turning long after it is set down. The quantum bounce in Ashtakar's description reaches its minimum and begins its outward movement, and the universe smaller than an atom grows, and the growth continues, and billions of years pass in the expansion, and stars form and die, and their remnants drift, and galaxies move apart, and the light from the earliest moments of the expansion travels outward across a distance that is itself expanding, and all of it is part of a process that the bounce did not begin, that the bounce rather continued, the way a river continues past a particular stone without the stone being the river's source. The ice is still curving beneath the traveler's feet. The south is still somewhere ahead, receding as the curve continues, remaining always ahead because the geometry of the surface does not bring a southern wall into existence, simply because it is being searched for. The traveler moves, the ice holds. The universe expands outward from a quantum bounce that was itself the result of a prior contraction, which was itself the result of a prior expansion, which had its own prior bounce, and so on, the chain extending backward through time in a sequence that the mathematics does not require to have a first link. There is a quietness to that picture if it is held for a moment without urgency, not the quietness of an answer that has resolved everything, but the quietness of a description that has stopped requiring what it was looking for. The beginning that was being searched for is like the southern wall. Its absence is not an incompleteness in the landscape. It is a fact about the geometry. The universe does not need a first moment, for the same reason that a sphere does not need a southernmost edge. The structure does not provide a location for one. The structure simply continues. The universe, smaller than an atom, at the moment of the quantum bounce, is already expanding. It has already passed through the minimum. The density is falling from 5.5 times 10 to the 96th kilograms per cubic meter, and will continue to fall for the next several billion years as the expansion carries matter and energy into ever larger volumes of space. The falling is smooth. The equations hold through the bounce. The prior contraction is behind the transition point, and the expansion is ahead of it, and the transition itself is a moment in a process that stretches in both directions without requiring a boundary in either. The universe continues outward from that moment as naturally as light continues outward from a lamp, not because something launched it, but because that is what expansion does. And this expansion, like the others before it in the sequence, is simply continuing what the structure of space-time makes possible. The Antarctic ice curves away in all directions. The traveler's skis move over it in the quiet of the polar dark, the breath-making small clouds in the air, the stars in the southern sky, the same stars visible from the north but arranged differently, unfamiliar in their positions, the familiar constellations absent or inverted. The ice continues. The question of where the edge is does not resolve into a discovery. It resolves into a description. There is no edge here. The geometry does not contain one.